Hello, my name is Caleb Harris, and this is my Lab 3 for Physics 2212, Magnetic Field of a Bar Magnet. Next is the introduction, physics principles, and results. The last purpose was to observe and better understand magnetic fields through visual representation, to visually observe the relationship between distance and magnetic field, and to use the distance dependence of magnetic fields in the Biot-Savart law to find the magnetic moment of a bar magnet. The physics principles are the Biot-Savart law and the magnetic dipole moment. Results are mu is equal to 2.21 amps times meters squared, and n is equal to negative 3.2971. For models and assumptions included, I assumed the bar magnet acted as a magnetic dipole, and the main model was the Biot-Savart law, as you can see on the right. In addition, I also included the slope formula, slope-intercept form y equals mx plus b, which when m is the slope. Well, in my previous slide, it was the n, and m is the slope of my line. For my system and surroundings, initial conditions, my system was a bar magnet, and the surroundings was everything else in the universe. Initial conditions was the bar magnet and the magnetometer on my phone. And the experiment consisted of the location of the magnetometer on the phone was pinpointed by sliding the phone perpendicularly to the ruler, both vertically then horizontally, with the bar magnet on one end of the ruler to see the position of the phone relative to the magnet. The strongest magnetic field was being read. Then on the on-axis distance, from the bar magnet to the magnetometer was found using the ruler for several different magnetic field values. These are my observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The position of the phone matters in terms of ensuring that the magnetic field of the Earth does not interfere with our readings for the magnetic field of the bar magnet. Alright, for my code, I first created a cylinder to represent the magnet at the origin. Then I defined a function for the magnetic field relative to any position around the magnet, which you can see on the code on the left. In the middle, I created an observation. The code in the middle I created 6 observation locations, 2 of them being on axis and 4 of them being perpendicular. I then edited the code to add the axis and magnitudes. Finally, the code on the right helped me create the rest of the arrows for perpendicular and on-axis observation locations. Make sure that the magnitudes and the directions of the arrows were accurate. Lastly, I created an arrow representing the magnitude and direction of the observation location that is 45 degrees off the axis. This is the model for my code representing the magnitudes and directions of the magnetic fields at the on-axis and perpendicular locations. As you can see, I have my two blue arrows being perpendicular, and I have the 2 orange arrows being on-axis. Both of the orange arrows pointing in the same direction as well. And then the one purple arrow is the 45 degrees off axis. Here's my data. As you can see, with my filled in Excel charts, as well as my graph, which gives me my slope. And I also want to point to the formulas on the right. The ln of bx equals to ln of k plus n ln of r. As you see from the earlier model, it's very reminiscent to the y equals mx plus b, which I said allowed me to create the formula. And like I said, my slope was given to be negative 3.2971, and the full formula was that y equals negative 3.2971x minus 15.359. The main source of error could be that the location of the magnetometer on the phone may not have been found precisely, resulting in a significant margin of error. This would skew the distance results from bar magnet to the magnetometer. If the reading of the magnetometer did not match Earth's magnetic field before the experiment began exactly, that may have skewed off-axis results of the bar magnet's magnetic field. And more than likely, there are no discrepancies as a bar magnet's magnetic field models that of a magnetic dipole. For the first what-if question, if I hadn't oriented the experiment to compensate for the magnetic field, then my results would have been less accurate. The Earth's magnetic field would skew my readings. I would have to adjust my experiment by subtracting the Earth's magnetic field from the total magnetic field. For the second what-if question, my results would have likely doubled because the measurements at each location would double. To conclude, the Biot-Savart law and its distance dependence can be applied to bar magnets with accurate results. Bar magnets can be used to accurately model magnetic dipoles, and distance is the very important factor to consider in determining the strength of a magnetic field. Thank you.